Perfect. As the second speaker is going to be Daniil, who's a PhD student here at École Polytechnique under supervision of Eric Moulin, and who is going to talk about regularized reinforcement learning.
Yeah, thank you very much for presentation. I will talk about our recent ICLR paper that will be presented in several weeks. So the main idea of this paper and what we are going to show here is that kind of similar thing, a little bit with the point of that typically in real life we have not only a kind of environment, we don't have only our machine learning problem, but also we have additional data. And the question how to utilize this data in some efficient way. And in this work, we kind of not really proposed, but we analyzed properly one of the simple way to use existing data of expert demonstrations into the learner just by things that we call demonstration regularization. So I will talk about it a little bit later. And also the second thing that we have done is that if additionally, as happens in emerging applications of RL to large language models, we don't have our real rewards at all. And we can somehow extract them from human preferences. And it turns out that this framework that we will present, first thing is we will just completely coincide with the existing framework of fine-tuning LLMs. And it allows to efficiently utilize both human preferences and expert data. And as a byproduct of what we are doing, there will be some guarantees for behavioral cloning, some guarantees for rigorous RL, etc. So let's get started. So first of all, it's the most classical picture that appears in all talks about RL. It's about what we will talk about. So in RL, we have our environment, we somehow interact with it, and that's it. So our goal as agent, in our case, for example, it will be large language model, it will generate some tokens, it will be our actions, and our state is the current state of our sentence that we are trying to generate. And we get some rewards during the course of training. And the modern applications of RL are a little bit beyond this model of just interaction with environment. For example, in the InstructGPT pipeline, we have not just using reinforcement learning, but also we have a lot of additional stages before this framework. And it's the question how it interacts with actual learning algorithm, because kind of just pure RL theory studies only step 3 in this pipeline. But this pipeline consists of several steps. I will discuss them later in more detail. But so it's the kind of was the main motivation of this paper. So that in real life, we have also data of different type, how to utilize it properly. And I will start from some preliminaries. So we will study some learning process in MDP. For example, finite horizon. In case of LLMs, it's, for example, finite length for generation. You have some state space. It could be infinite, for example. You have finite action space. It's needed for a lot of technicalities to be finite. And finite horizon, that's finite number of steps in one game. Also, we have kernels that we assume to depend on H, and rewards that also will be assumed to be depend on H. We have standard definitions of value, standard definitions of Q value, that are just sum of rewards to the end of trajectory starting from our current step. One of them may be different, that's from very standard RL things, that it depends on actual step, H, because we are considering a finite horizon setting. And also, yeah, I will recall and with a little bit of notation. For example, some unusual notation here typically is this product. Multiply our kernel with any function of states and evaluate it as state action as A. That's how it should be read. And we have Bellman equations, optimal Bellman equations, standard formulas that describes optimality and our current value in MDP. And our goal is to find some policy that we want to be, epsilon optimal. That means that its value is in distance epsilon from the optimal value, and at the same time minimize number of interactions with MDP. So we have some MDP we can interact with, we can take some policy, run this policy for this environment, get some data, and we want to minimize number of interactions. But yeah, as I said previously, in real life, we also have a lot of expert data. For example, in robotics, kind of the expert data is, for example, demonstrations how human just make their steps, how they go on, and it's also possible to utilize this data during the learning. So for this moment, we will additionally assume to all the standard array paradigm that we have some expert demonstration data set that consists of trajectories of finite length without any rewards, but we assume that they was generated by some expert that should be good enough in what he is doing.
This is different than model-based reinforcement learning.
Yes.
Okay. So you just have like some benchmark that you trust, and then you want to try to adapt to.
Yeah, even I don't have access to this policy itself. I only have some data set and nothing else. I cannot generate new samples from this data set.
Okay.
For example, in case of LLMs, that means that we have good text that was written by human, but we don't have kind of actual language model that goes beyond this process of writing text by human.
Okay, thanks.
Yeah, and here I will introduce this very simple framework how to do it. Actually, first thing that we want to do, we want to somehow aggregate the information about the data set. And the simplest thing that we can do, we can just try to reconstruct expert policy given this data. We can try to reconstruct what expert is doing given this interactions that was presented to us. And it could be done by things that called behavioral cloning. So actually, we're just trying to maximize likelihood of the actions that was taken by expert in given states, and that's it. We're just trying to do maximum likelihood of the actions of the expert given states of expert, with additional regularization to make it process stable. And afterwards, we add to RL process additional regularization to keep our agent close to this behavioral clone policy. We want to make it very close to expert policy, but we don't have expert policy, so we will learn some surrogate for it and try to be close to it. So, and we will just add this regularization to the learning process with such an aggregated data. We end up with such a guarantees. The main thing, so this thing is a little bit disastrous, but it's not the main point. The main point is that here says the standard rate for ORL is 1/epsilon squared, as everywhere in statistics. But here we have additional n factor. And basically it means that if we have large enough expert data set, we just need less interactions with environments. That make a lot of sense. But previously it was not known how to do it with some simple framework. So because all the existing frameworks requires to somehow introduce this expert demonstration to the algorithm itself and change the algorithm for doing array. But here we just take out of shelf algorithm for array with regularization, and that's it. So, and we have such an acceleration of what's going on. And I will a little bit describe the ingredients, how to make this result. For example, what we know about behavioral cloning and what we want to have from it. What we want to have some statistical guarantees of reconstruction of this expert, basically. And in this very special thing that's called trajectory Kullback-Leibler divergence, it is such an expectation of Keil divergence. But you can, for example, take a look on this guy and take a look on this guy. Understand that they kind of very close to each other, because basically our log loss for maximum likelihood estimation, it's almost Kullback-Leibler divergence up to additional entropy term of our expert. So that means that this behavioral cloning, it's basically try to optimize this trajectory Kullback-Leibler divergence given some unbiased estimate of it. So yeah, and for example, if we consider only finite MDPs and everything in this case, and class, for example, for almost all policies, we just a little bit separated from zero to not have a lot of consequences of dividing by zero in Keil divergence. That always happen, because here we have this thing is in denominator. That means that if we have policy equal to zero, this Keil divergence can explode, unfortunately. But if we don't have such a behavior, for example, we optimize only over class of policies separated from zero, then we have fast rates of estimation of this Keil divergence. That's makes sense, because Keil divergence is something quadratic by Pinsker inequality. And that means that for Keil divergence, we have estimation of order some dimension over n. And this dimension notion can be extended not only in finite MDPs, but in some linear MDPs or something more general. So for Keil divergence, we have kind of fast rates of convergence. That's the first observation to make. And this thing is optimal. So it's easy to construct minimax lower bounds. It shows that, okay, we cannot basically improve it. The dimension over n is unavoidable. And afterwards, we have guarantees for the first step. Afterwards, we need guarantees for the second step. To do it, we need to dig a little bit into what's going on in this regularized vote. And here we can define such a additional value. That's our usual value minus this regularization that we was talking about. And basically, this trajectory Keil divergence is so good that it's decomposed. It's something that will look like the Bellman equations. That will be actually Bellman equations with additional regularization here. So, and since we have Bellman equations, we can run, we can try to approximate optimal Bellman equations. It looks like that. So we just decompose it step by step. And what we are doing, the only thing that changed from usual RL here is that when we compute optimal value and we will compute optimal policy, we have additional Keil regularization with respect to our behavior clone policy. So we are trying at the same time optimize value and not go too far from the result of estimation of expert. And for this type of problem, it's possible to develop algorithm with convergence of order 1 over lambda epsilon, where lambda is regularization parameter. So if we have very large regularization, that means that our policy should be very close to this behavioral clone policy. We should not learn too much, because it's kind of obvious what we should be answering. But if lambda is very small, it's a hard problem. It's the same hardness as usual array. So the value of this lambda is very important everywhere. And basically, if lambda is large, we have acceleration. We need less interactions to get good policy. And basically, what we have some expert that we assume that will be good enough. Means that it will be some epsilon optimum. We assume that our behavioral cloning goes very well, that this error of behavioral cloning affords some another epsilon. And by some very straightforward computations can be shown that all the error of this process can be decomposed as three errors: error of expert, error of our optimization in array, and this our error of regularization. It's our bias that we introduced when it was doing regularization. It's just upper bound on this guy multiplied by lambda.
How do you get the second term?
Second error.
Have you regularized in the second two? Does the second term already pops out of the regularization? Yes, because you have lambda,
yes,
right?
yes.
Okay.
So here I just moving from this original values, I regularized both values at the same time.
Yeah.
But since one of the sign plus, one of the sign minus, I need to pay something like that. And afterwards, I pay my error for regularization.
Yeah, and that thing also depends on lambda.
Yeah.
On lambda. Yeah.
Yeah, but it's some complexity depends on lambda. But so we can, for example, run algorithm a little bit longer if we have smaller lambda to have the same level of error. Yeah, but this thing, yes, indeed, it depends on a lambda very implicitly. But for example, if we take optimal lambda from point of view of this error, this lambda have this following order. It's epsilon that we want from RL algorithm over squared error of Kell divergence. It's kind of the lambda to make this thing of kind of same order, this thing and this thing. But in this case, since our Kell divergence error is for the 1 over square root of n, this makes it, if we just plug in it in this trivial estimate 1 over epsilon lambda, we will end up with some acceleration. So the result is kind of not rocket science from point of view that he has not kind of something very unusual or strange. It's a combination of several ingredients as it was particularly done in several applications. So, and afterwards, I will move to something close to what we have discussed. So this framework with this regularization, I will describe it once again. First of all, we have our data. We somehow extract information from this data by behavioral cloning. Just try to learn policy that will mimic expert. And we add regularization to keep close to this policy. That's it. And this simple trick allows us to improve speed of convergence of our algorithm. From point of view, if we have a lot of data, we accelerate convergence. That's if we don't have any data, it's better just to drop all this data. So that's also makes sense since it cannot harm, not help you. So sometimes it's more reasonable to drop it. But right now, you move to the settings, then it's even if we have small amount of data, it's better not to drop it. So let's consider the case of learning from human preferences. In this case, there exists some true reward function, but we don't know it, and we don't get any reward signals during our interactions. But we have another type, another way how to get our rewards, how to understand what was the reward of trajectory that we generated. So here I introduce a little bit of notation. So reward of tau is the sum of rewards through the trajectory. It makes sense. And basically I will return to this back. And the assumption is the following. So we have for two trajectories, we can generate two trajectories anyway, how generated. And we have some preferences of one trajectory over other trajectory, or over another one. It will be just some Bernoulli random variable with some parameter that is some function, typically sigmoid function, of difference between rewards. So we have some statistical model over rewards. We are not sure how this rewards looks like, but we have some statistical model that describes the behavior of these rewards. And also we need some technical assumptions to make it in some sense invertible, to be sure that we can reconstruct these rewards if we reconstruct these preferences. And the most well-known model here is predatory model when we take this sigma function, a sigmoid function. So it is the most used model in the practice. And basically what we end up it will look like exactly like this InstructGPT pipeline in the very end of the day. In the very beginning, what we are doing, we collect some demonstration data and train some supervised policy. In our case, we are doing behavioral cloning over expert demonstrations. Afterwards, we collect some comparison data and train reward model. So we need to collect some additional data in order to be able to somehow evaluate our rewards. And we just, for example, can take the policy from the previous step. That's the most classical choice. It was described in InstructGPT paper, that we just take this policy, previous one, generate trajectories, evaluate them, get it enough times, reconstruct the reward model, and afterwards we will learn our optimal policy given this reward model and with additional rigorization. That's the pipeline that was described in absolutely practical paper. And on the language that I was describing, it looks like that. So first of all, I'm doing this stage one with behavioral cloning. Afterwards, so this stage of preference collection looks like that. So we fix some policy PS as a behavioral clone policy and collect some data set of preferences afterwards. So we generate two trajectories, and afterwards we ask some human to evaluate what is better. Given all this data, we compute some just maximum likelihood estimate of these rewards without anything specific, without anything in addition, just do maximum likelihood. And so for regularized RL, we just plug in our head as our real rewards and regularization with respect to behavioral clone policy. So, and it turns out that the first thing that I was described already, that this pipeline exactly corresponds to what people do for LLMs. And the second one, this pipeline is provably efficient. So it turns out that if we have, so I here a little bit simplified the condition of this theorem, but if we have large enough data set for reward model and kind of moderately sized, I would say, expert data set, then this framework will give us epsilon optimal policy, for example, infinite or linear MDPs. So the simplest cases to analyze from point of view of RL. In this case, we will have guarantees the same as we have the true rewards. The only condition that we need large enough this data set. And basically it makes a little bit of contrast with the previous results. So in previously described results, that was done in Michael's team as the following. So we have some data sets. We don't know the source of this data set, but we have some data set. And we learn reward model given this data set. So kind of we was given some data set, we learn reward model, and afterwards we just directly maximize this reward. Just it's h equal to 1, just bandit setting. We removed all the array complications from here, just usual bandits. And it turns out that for any size of this data set, there exists some bandit instance that it's probably inefficient. Then we can have some concept of optimality for this way. If we just do maximum likelihood without any rigorization, without introduction of any type of pessimism to the reward estimation. And the remedy that was proposed in the paper that I'm talking about was to do some another estimation of rewards, some kind of pessimistic maximum likelihood that is not so feasible as just doing rigorization with respect to some known policy. And basically, kind of the main things that we have shown that if you just do the full pipeline, not excluding any step, it will be efficient. If you exclude first step, it may be inefficient, as shown here. If you have all these 3 steps that was done in practice, it's probably efficient. And that's all for today.
Thank you.
So, thank you very much.
Are there any questions? I may have one on the first part. Like you said that if you have this your lambda that is this ratio between errors, then you are optimal. But practically, like I don't see how would you tune? How would you find lambda? Would you?
It's a rather good question. So because in practice, yeah, we really don't know this real error that we have in this expectations, things like that. So the only kind of remedy that I can suggest is to just take it something like just we know that k divergence should be order 1/n. We can just scale with size of data set and something like that. But in practice, people just take lambda equal to 0.1 and it works.
Okay.
So that's
yeah. So the fine tuning like on the kind of data set that you have maybe.
Yeah. So it's yeah. So that's very good point. That's yeah. Actually, we don't know this optimal lambda, and we need to somehow tune it, and it requires knowledge of some unknown constants. So that's classical problem also of optimization. That appears that we don't know the Lipschitz constant of what we're optimizing, or if we even know it, it's absolutely useless. Yeah, so
it still works. Yeah, I understand. And have you tried like working on? If, for example, you take another algorithm, you don't go like with Bellman recursion, maybe you take another algorithm of like a recursive learning. Would you think that this still kind of analysis that you have considered can still work?
So I'm kind of the crucial thing in the analysis basically is such type of convergence for rigorous RL. So one over lambda epsilon. So and I'm not aware of any other type of analysis that will not go through this Bellman equation stuff that will have such a rate that will include also exploration problem. So there exists some works in policy optimization that they assume that we have kind of access to true policy gradients. In this case, they can achieve such a rate of convergence.
Okay. Thank you. Well, there are no more questions. Like, thank you very much, Daniel. And so it's all for today, and see you in 1 month, less than 1 month actually, for the last session before the summer break. Bye bye.